we'll start just going over some main ideas, right? So we'll start with gravitation. Again, I'll upload all this stuff. So if you want to follow along, copy stuff, that's fine. But I'd rather you try and pay attention to kind of the big picture, right? So here we're talking about chapter 13. Most of it, pretty much everything except for gravitational potential energy. Okay, we'll get to that idea later on. So main thing, force of gravity is equal to big G m1 m2 over r squared, that r hat. Okay. Now again, if you look at the equation sheet, let's compare it to the way they wrote it in the equation sheet. In the equation sheet, and I believe this is the most recent version, they give you just the magnitude, okay? So they don't exactly write it in vector notation, but understand that that r hat is just to represent the direction of your force, force of gravity, which means you gotta make sure that when you're trying to calculate the force of gravity, you break it down into its components when you need to. Okay, x component, y component, that kind of thing. Okay, so that's just, Newton's law of gravitation. It's an inverse square law. A lot of questions you'll see tend to be regarding how it's proportional to the mass, inversely proportional to r squared, and that it's really weak. Okay, so that G 6.67 times 10 to the negative 11 newtons meter squared per kilogram squared. It's really weak, right? It's really weak. Okay. So then, a big part of gravitation 2 is understanding Kepler's laws. Okay, and we had a couple derivations with Kepler's laws. I remember. Look back at the notes that I had from before. Okay, so again, as far as studying strategies, when I think about the times that I was successful in college and the times that I was not, take notes of your notes. It seems kind of weird, but when you take notes from reading or from class, they tend to be pretty scattered because you're learning in a progression and you're just trying to take all the information, and from there, when you take notes of your notes, you're really trying to look through and look for connections between each individual thing, right? I think the big part about physics is making those connections, looking at this giant list of equations and being able to see how they're all related. Pretty much every single thing here is connected to some other thing in some way. And so when you take notes of your notes, you look for those connections and you try to distill it down, right? So when I gave you these notes before, I try to give you everything, but some of the main takeaways that we got to was, for example, we started talking about circular orbits, right? So circular orbits is a special case, but it's a very common case that we investigate for AP. So circular orbits, or we talked about elliptical orbits. Let's look at some of the differences in the outcomes. Now again, circular orbits are a special case of elliptical orbits, but we can do a lot more math with the circular orbits. We can't really do as much math with the elliptical. So generally speaking, okay, you can say that the square of the period is proportional to the cube of the semi-major axis. But again, in terms of making a more exact mathematical statement, that's kind of hard to say for elliptical. But for circular, by looking at circular orbits, seeing how the acceleration is purely centripetal, and kind of using our circular motion knowledge, we can kind of work out some of that information. We get that the tangential velocity for a circular orbit is equal to gm, I'm going to use capital M over r. Okay, capital M is like the mass of the main body, the planet. You'll find that for a lot of the problems that we deal with, you usually have one really, really massive body and then a really, really small body. You're not really dealing with like binary stars or anything like that. You're not going to work with that. Okay, so from this, using some of our circular motion knowledge, that tangential velocity is related to your angular velocity, and how your angular velocity is related to your frequency, and then your frequency is related to your period. When you start substituting things in, we can work out some connection between these constants and the period as well, right? So if I kind of make this substitution, and then I make this substitution, and this one actually really should make sense. You're basically taking the circumference of your circle and dividing by the time it takes to travel that circle, and so of course that's going to be your tangential velocity. But when you substitute it onto the left-hand side, you're going to get 2 pi r over t equals to gm r. Okay, I'm taking this, I'm substituting it in for this. Okay, I know here. Let's be consistent. I'll use capital R here. It's essentially the same idea, right? What is the radius of this circular path that you're taking? That's r. Okay, and we're gonna solve for t. What we're trying to do is right now we're trying to demonstrate Kepler's third law again, that the square of the period is proportional to the cube of that semi-major axis. With the circular orbit, that semi-major axis is your radius. So we'll get, let's see, you'll get like a 2 pi r square root r over gm equals to t. Or if you square both sides, you can get 4 pi squared over gm r cubed equals to t squared. Okay, so this is specifically for circular orbit, right? So for elliptical orbit, you know, we can't really make an equal sign. I can't tell you. If I told you what the semi-major axis is, you couldn't tell me what exactly the period ought to be. You can only determine that if I change the semi-major axis, how would the period change? But for circular orbits, you can actually calculate it all the way out. If I tell you the period, you should be able to figure out the radius or mass of the planet that will lead to that period, or vice versa. I give you the mass and I give you the distance of your orbit, and you should be able to figure out the period of that orbit. Okay. This one, I know there's kind of a whole host of equations that are not on the equation sheet but are kind of good to memorize. Really, you should know how to derive this. You can try and memorize it, but this is the one that you kind of want to know how to derive, because there's a lot of questions on the AP exam that come up where they'll tweak something in between. They'll make some slight change in the in-between steps. And so then this doesn't work out exactly the same or something like that. And so you kind of want to be able to fit those changes into your derivation as you go. and also sometimes they just ask you to like work it out, right, to show it. So okay, so again, this stuff, this is all third law. I don't think on the AP exam they really say anything like, what is the third law? I don't think they ask for anything that specific, but it's one of Kepler's laws. Okay, so first law is just that all orbits are conic sections, right? That was the first law. It could be a circle, it could be an ellipse, it could be a parabola, which is when you reach escape velocity. It could be a hyperbola, which means you're like way past escape velocity. And then the second law was a comment about the conservation of angular momentum. Okay, so it says that a satellite sweeps equal areas in equal time. Okay, basically what it means is that it's a conservation of angular momentum. Okay, and so what it means is that when you get closer, you go faster. When you're farther, you go slower. Right? That's really the main idea. And that there are 2 points that are particularly important to know about. That is the periapsis, which is the closest approach, and the the apsis. I've seen it actually. I've seen apsis and I've seen apoapsis. I think I'm not sure why they're if one is more correct than the other. I've seen both. This is the furthest approach. And those 2 points are important because when you look at any elliptical orbit, those 2 points are always perpendicular to the line that connects it to the body. Okay, they're perpendicular. That makes them very useful points for analyzing angular momentum, because when we look at angular momentum of orbits, oftentimes we use r cross p, which is like r cross nv, and that for these points, these 2 points, because it's at 90 degrees, it works out really nice that your angular momentum is just r and v. Right? Because when you take the cross product, you're looking for how much is one vector perpendicular to the other vector. At those 2 points, they are perfectly perpendicular. And so it's a good spot to be like, okay, well, this is how far away the periapsis is. I know what my angular momentum is. I can figure out how fast I should be going. Or if I know how fast it's going, then I can figure out what the angular momentum is. And that angular momentum must be constant the whole trip. So that angular momentum is the same out here as it is back here, which is why as my radius or my distance increases, my velocity goes down. Right? Okay. Any questions about gravity? That's pretty much it. Okay, so Newton's law, gravitation, very much like Coulomb's law, and then Kepler's laws. So Kepler's laws is probably the more unique part of gravitation, knowing orbits and so on and so forth. We talked about Hohmann transfers too, right? A little bit. Talk about how you go from one orbit to another orbit. Let's look at that real quick, just for complete. So when we talk about the Hohmann transfer, I don't think this is in the book. It didn't call it the Hohmann transfer in the book, but it does actually cover it in the book. I remember. And I've seen this come up on the AP exam like 1 year. It's pretty specific. So, yeah. It's on page 370. if you want to look it up. Right? So when you look at this diagram, this is how you can transfer from one circular orbit to another circular orbit. You have the inner one, the smaller circular orbit. What you do is you do 2 boosts. You do 1 boost, and the main idea here really isn't just knowing the transfer, it's understanding why it works. When you do a boost, what you're doing is you're increasing your velocity at this altitude that is now too fast to maintain a circular orbit in this altitude. You will take a wider turn than the circular orbit would have, right? You overshoot your circular orbit. But because you start going further away, by conservation of angular momentum, you start losing speed. And as you lose speed, you are now entering altitudes where you're not going fast enough to maintain your circular orbit, right? So now you can see it takes too sharp of a turn and starts going back down. That's why it's an ellipse. So what you do is once you get to the peak, you try and set your boost so that the peak of this elliptical orbit is tangent to the next circular orbit you're interested in entering. So that at that point, then you do a second boost to turn this elliptical orbit into a circular orbit. Okay. So you can go both ways. Either you're trying to enter a higher altitude, so you do a boost, and then you get higher, and then you do a second boost to enter a circular orbit. Or if you want to drop, you slow down. You do like a reverse thrust, right? You slow yourself down, that drops you to a lower orbit, and then you do a second slow to maintain that circular orbit, right? So it goes either way. And so this is how you can kind of transfer between orbits. Most of the time you want to do circular orbits because when you have elliptical orbits, you know, you're speeding up, you're slowing down. That tends to be very difficult to manage whatever it is you're doing. So, okay. So yeah, just kind of, I suggest if you're wondering about that, look that up. In the book, it talks about it from the perspective of energy. You can look at it in terms of conservation of energy too, because there's no, well, there's usually minimal dissipative forces. There's usually actually drag, but whatever. Okay, so that's gravity. Looking back at okay, looking back at electricity or electrostatics. Okay, so when we're talking about electrostatics, and this was chapter 25 and 26. All of chapter 25 and 26. I'm pretty much going to jump right into the review packet that I gave you, so you can kind of take a look. I think this diagram is a pretty good flow chart of the things you need to know. Okay. So when we talk about electrostatics, that means we're talking about charges that are not moving. When charges start moving, things get really, really complicated. So everything that we do here is assuming equilibrium, or somehow my charges are fixed, or if they are moving, well, we're kind of only looking at the electric effects. But let's go through kind of the different categories when you're looking at the basics, right? Make sure you understand the difference between insulators and conductors. Make sure you understand how we measure charge distributions. Talk about linear density, surface density. They use sigma here, but in the book we used eta. I think I've kind of seen both. So in the book we used eta. This one's eta. This one here is sigma, lowercase sigma. Kind of seen both. Okay, but they mean the same thing. We're talking about surface charge density. And then there's volume charge density rho. Okay. Some of the main ideas from Coulomb's law, right? Like charges repel, opposite charges attract. make sure you understand how this shows up mathematically. Okay? In other words, in Coulomb's law, when you're looking at this, right? How is the like charges repel and opposite charges attract work out mathematically? It's because if these two are positive, your R and your F are in the same direction, right? Whereas if they have the opposite sign, then they are pointing in opposite directions. So in terms of actually calculating the forces due to Coulomb's law, make sure you know how to do it for point charges. How do you do it for continuous charges? There are two particular types, arrangements, or geometries that we look at, a line of charge and a ring of charge. Even for the ring of charge, it's kind of, I guess the ring of charge is good to know because aside from the line and the ring, there really aren't other shapes that have good symmetry. So look at those ones. Again, those examples are in the book. And then, yeah, use to calculate force between charges. I think that's pretty straightforward. Looking at fields. Okay, so when you're looking at a field, your field is the force divided by the test charge that you put in that field. And so you can kind of break it down into an effect that is due to kind of like a your source charge, right? So we can I call this QS. Actually, I think sometimes what they'll do is they'll use like a capital Q and a lowercase q. So capital Q would be like the main one, and lowercase q would be like the test one that you put in the presence of the other one. But maybe you can use QS and QT or something like that, or however you want to do it. There's a test charge and there's a source charge. Source charge is the one you usually look at as being the thing that's creating the field, and then you put the test charge there, and the test charge moves around based in the presence of that field. Okay, so make sure you understand how field diagrams work. So field diagrams are just diagrams. It's understood that the field is present everywhere in space, but in a diagram you can't draw an infinite number of arrows, so you just diagram with a few arrows. Usually, the closer the arrows are together, the more concentrated the field is. Okay, so usually, the closer the arrows, the more concentration, more concentrated. Or in other words, the stronger the field is. Right? So if you have a bunch of arrows put together, then close together, then it's stronger. You need to make sure you know how to determine the force of a charge that you put in a field. And then when we look at the graphs of electric field, there's a couple, right? There was, okay, if you have a point charge, it's an inverse square pattern. If you have a line of charge, it's an inverse pattern. If you have a plane of charge, it's a constant pattern. You need to know those. Okay. We haven't gotten to Gauss's law yet, so don't worry about that. Okay, we haven't gotten to Gauss's law yet. So ignore this, and we'll get to that. This is really important, but we'll get to that later. Okay? You just need to make sure you understand this set of stuff. Okay? So, there was one problem that I had put up. I want to go over it. And again, for the time being, when we do these continuous distributions of charge, okay, you're not expected to actually complete the integral yet. I just want to make sure you guys know how to set up the integral. That's what I'm testing on. Make sure you know how to set it up. Actually, we can try one of the ones in here. Right, so if you turn to go ahead and turn to this page. Okay. It says page 12. They're not necessarily in order, so you'll have to kind of go through them a little bit. Okay. So, oh, I think I left off the, sorry, hold on a second. Okay, let's go through some problem-solving steps here, some strategies as to, again, how do you figure out what the electric field is due to a continuous distribution of charge? Okay, so what we want to do first is try and establish a relationship in our slices. How are we going to chop this up? If here's this ring, okay, and we take a little bit, some delta Q, okay, take a slice. What we want to know is how does delta Q relate to a some sort of trying to think, like a positional measurement, like a, well, actually, I guess in this case, you kind of have to look at whether each slice creates a different field at the point that you're interested in. I think that is probably the more important starting point. In this particular case, I guess this is maybe not the best example, but in this particular case, each charge actually is the exact same distance, right, from this spot. Whereas sometimes it's not. So you kind of have to determine whether, so determine if each delta Q has a different E sub I. Right. What I mean by that is, do each point create a different electric field here? So if you compare this to like the line of charge, in the line of charge, each piece is a different distance, and then you're gonna see that they have different, each point has a different field there. If it does, relate delta Q to a delta, like some sort of delta X, right? Because what you want to do is eventually you're going to want to take your charge and relate it to how your object is geometrically cut up, right? Some sort of spatial thing. Usually it will be like a delta Q over delta X equals to some sort of big Q over some big L, which is equal to some sort of density, charge density. Yeah, that's fine. Okay. In this case, E is the same everywhere. Okay, it's the same for each piece because they're all the same distance, and if you chop it up into delta Q's, they all have the same charge, right? So Okay. I guess in this case, it's in this particular problem, it says, suppose that charge Q is distributed evenly around a ring of radius A in the YZ plane centered at the origin. Find the electric force on the charge Q. The easier way, honestly, is not to just straight up look for the force on charge Q. Look for the E. What is the electric field at this point? If you can find the electric field at that point, then it becomes really easy to find what the force would be on the charge. So we'll start there. Okay. Step 2, use symmetry to find the important components of E sub I. Okay, use symmetry to find the important components of E sub I. In other words, in this case, when we look at the symmetry, we find that this electric field may point down at some angle, but from another slice on the exact opposite side, right, does the same thing. And we find that they will cancel in the y direction, and if you pick one from this side, it will cancel in the z direction, so that the only thing left is what's coming out in the x direction. Right? Yep. Yeah, so because you have charges coming out of the page and into the page, if you can kind of envision what this is trying to diagram, if this ring is kind of shown to be tilted, but if it were perfectly flat, right, some of it is in the z, some of it is in negative z. Either way, if this was, are you saying if this was a positive charge or negative charge? If this is a positive charge and this is positively charged, it would push away. Let's say like you have you're investigating this particular element on this side of z. Then it would push this charge in the negative z direction. But there's also a charge on this side of equal amount pushing in the positive z direction. And so the z components will cancel out. If it is negatively charged, then it will attract, and this element would attract in the z direction. But again, there's an element on the other side attracting in the negative z direction. In the end, it will either repel or attract in the x direction, but the main point is that there's nothing balancing out the effects in the x direction, only balancing out in the y and in the z. Whether it attracts or repels depends on what the charge is. So first, let's figure out what E is, the E net. And then once we put a charge in there, we can figure out where it goes. Good question. Okay, so using this symmetry, we find that we really just want E net, or whoops, we just want EI in the x. Okay, so what is EI in the x? This will equal to EI cosine. Well, actually, here let's look at the magnitudes. At this point, since we're already breaking down into components, yeah, sorry, let me cross all that out. We're not really looking at vectors anymore. We're looking at components, so we'll just do EI in the x, which is just the magnitude of EI. In other words, the magnitude of this electric field from this element. And if this is angle theta, then we want cosine of theta. Okay. And again, in this case, as we go through and we look, every element will have the same angle theta. They will all have the same angle theta. because they're all the same distance away from the axis and the same distance away from the point. Okay. Okay, so at this point, a lot of times what we want to do is we don't want to use theta. We want to try and get it again in terms of dimensional, like a distance, right? So how do we get cosine in terms of a or this distance x, or so on and so forth, right? That will become adjacent, which is like an x, divided by a hypotenuse, which will be like an a squared plus x squared. Does that make sense? Make sure you understand where this is coming from. Cosine is adjacent divided by hypotenuse. What we're determining is that this hypotenuse length will be a squared plus x squared, if this is the distance x. Oops. Right? This distance, a squared plus x squared, wherein this distance is x. So adjacent over hypotenuse. Okay. If we want, we could even sub in what E sub I is. Okay, so what's the magnitude of that electric field? That's going to be your K delta Q over that distance squared. Notice that the square root is gone because it's the square of the distance. And this is times x over a squared plus x squared. Okay. This is really the biggest part of getting to the integral. The part that I'm looking for you guys to learn how to do for now. Yep.
So, quick question. What's the difference between the lowercase q that we use with Coulomb's law and
it's completely arbitrary. There's no real big difference. You have to look at the context of the problem. Sometimes you use lowercase q, sometimes you use uppercase q. Usually uppercase q is going to be used for something that is constant, whereas lowercase q is usually used for a variable. So your test charge, you might put any number of, an unknown charge here. But this ring is predetermined. So I'm going to use uppercase q.
Okay, and then why are we using delta q?
Delta Q because we're looking at the charge, the electric field due to just that segment.
Oh, yeah. Right.
And not the full thing. Yeah. Good questions. Very, very good questions. Any other questions? Okay. So now we're going to find the sum. So E net is going to be the sum of these or we have some number of I guess if I were to be complete, it would be I equals 1 to some number, however many slices we want to make, right? The assumption here is that each slice is small enough to treat each slice like a point charge, but it doesn't really matter because in the end we're going to make an infinite number of slices. So we're trying to sum this. Okay? Questions on how to make this? Okay. From here, we can pull out any kind of constants. Okay, any kind of constants. So k is constant. In this case, each element is an x distance away, so that's actually not dependent on which piece you choose. Same thing with a. So we found that all of these are constant relative to what you're adding up. And so in this particular example, it works out that you're simply adding up the charges. Okay. Step 4, turn into integral. Okay, in this case, whatever your delta is what you're integrating with respect to. So this is all constant. So what I'm going to say is then that E net is equal to the limit as n goes to infinity of this sum and when you take that limit, that's when you get your integral. So the tricky part about sometimes doing these integrals is that we talk about limits of integration. In other words, what are you adding up? Okay. When you have a spatial dimension, it's very easy to figure out your limits of integration. In other words, you're trying to integrate from one end of a bar to another end of a bar. You integrate from 0 to 2 meters. You integrate from 0 to 5 meters, something like that. Or if you're integrating a bunch of angles, you can say you're integrating from 0 to pi or 0 to half pi. You know, it's easy to figure out how those slices work out. When you have something like charge, right, it's kind of hard to write out what that integration looks like other than you're trying to integrate the whole circle, right? Which is why oftentimes we don't want to try and do these integrals with respect to Q. But if we only end up with the integral of dq, or like sometimes we would integrate with respect to mass when we did center of mass or moments of inertia, if you can end up with just mass and you're just integrating with respect to that and there's no functions in there whatsoever, then it becomes pretty easy because basically it's just saying add up all your mass, right? Your step 5 is the step that I'm not concerned about for now. Whoops, your integral. That's really the last step, right? Calculate it out. But in this case, it's pretty straightforward. But I just want to make sure you guys can get to step 4. Okay? How do you create that? Can you do step 1 through 4? Then you're good. Okay, this is why you want to get to for now. Just make this. If you can just make this, you're good. Don't worry about solving it. Just set it up. It's the same thing with some of the other problems that we'll get to later. They'll ask you, can you set up a differential equation? But they don't ask you to solve it. Okay? Okay, so this is just one example. In terms of the tricks for how to create this, right? Sometimes if everything is the same distance away, everything's creating the same E, you're going to find yourself in a situation where everything's constant, pulls out, and you're just adding up all the charge, right? Your job is to figure out what this looks like. For a line of charge, what ended up happening is you had to take slices with respect to y, like this. You did these slices. Oops. So what you're going to end up with is some sort of delta y, and you need to relate that to your delta q so that then you can try and end up with some sort of integral with respect to dy instead of dq. Okay, so for this example, just as a hint, looking for function of y. Or function in terms of. Whereas sometimes you run into a problem that looks like this. Is not really a linear slice. What you end up with is more like angular slices. So now you have some sort of d theta or delta theta. How does delta theta relate to your delta q? Right? And then you want to try and get towards some sort of function in terms of theta. Okay, so your slices will tend to tell you what variable you want everything to be in terms of. Are you taking angular slices? Are you taking linear slices? Are you taking like surface slices, volumetric slices, so on and so forth? Okay. That's pretty much it. So, like I said, I want to save about 45 minutes for you guys to just try some of these problems. A couple things you can cross off as you go through this, because this is kind of a very general packet. So again, don't worry about the integrating part where it says integrate from bottom to top. If you can do it, go for it. If you think you know how to do it, or you want to take a hand at it, give it a shot. It's good practice now because it's something you're going to have to do later anyway. So same thing here. Says find electric force for a semicircle. A point charge is located at Q. What is the net force on it? Don't worry about finding the net force for now. Just derive an integral expression for E. Okay, just derive an integral expression for E. Don't worry about actually getting the final thing. Same thing here. It's a quarter circle, same idea. Just try and find the integral expression for E. All of this stuff is pretty good conceptual questions. On the very last page, when it starts talking about flux, stop here. Don't worry about flux yet. Everything else, though, you guys should be able to do. Hint, hint, wink, wink. I particularly like this question. This is a very nice question. To do. Okay. All right. Okay, so you want to retake.
Yeah, but first can I?
Yep, and then.
I don't particularly like
Oh, did you get the night? Yes. It was like a while ago. This was Aeolian, right? Yeah. Aeolian, Dorian, Phrygian. Wait, what? Aeolian is Lydian. Is 6. What's the first one? First one is Ionian. Oh. Ionian. Lydian. Dorian. Ionian, Dorian, Phrygian, Lydian. Mixed Lydian. And then a lot. So there's Aeolian and what's the last one? Loki. Okay. It's like just when you start C minus here without the
Oh.
lower switch.
Okay.
Wait. Yeah. Because when I played piano, I learned Phrygian, Lydian, and Dorian. Mixolydian. Wait, I did
Sure.
learn Dorian too. So Phrygian, Dorian, Lydian, Mixolydian. Those are the 4 I learned. It was long. I never learned Ionian or Locrian, but I heard about Ionian. Well, I mean, Ionian is just a skill. Oh. Okay, well then I knew that.
60% will work. Sorry.
Or no. Yeah. Well, that would be.
I just
why
updated this morning.
learned them because I already knew them.
That's right.
That makes sense. So basically, the only one I had no idea about was Locrian. Like I never even heard about it. Like I knew Ionian and Aeolian, but I guess I never made a connection if they were major.
Actually, I need to print some.
No one uses Locrian in songs. My teacher probably told me that, and I was just like, oh, never mind, I'll figure it out. That's. I mean, you don't need one. I don't need it. But Locrian, I.
I'll bring it to you. I have it.
X. Why are you doing this to me? Is this close? I don't know. You're close. No, keep going. Well, because I'm automatically breaking up into cosine of the sine. It's cosecant squared. Cosecant squared. Well, that's not. What's the tangent of secant squared? Cosine. I don't know. It's 1 over negative. Oh, 1 over. Is it just 1 over x minus 1? Why? Something like that. Why? Jeremy, you put Tetris. Dude, I'm like ranked like 30 something. Or it started yesterday. Oh, dude, I was watching you like pile up your pieces, and I was like cringing a little bit because you built like a super high tower in the middle. I don't even. I just take it. I just take it slow. I prefer playing on just like well, I mean, I don't like the stress of having like stuff really up there. I think it's fun. Like yesterday I started and I played for like an hour. I feel you. You're gonna be you're gonna be staying up till like 1 playing that game. I promise. I'll never stay up till 1 because I have stamina. Stop. Stop. Okay, we're done. Oh, magic. Sorry. He's hot. This is deep though. I kind of hurt. That hurt my neck. No. I was like pretending to be deep though. That hurt my neck. No, because I was being weird, and then I was like, this is deep. Hurt my neck. Yeah, he's like, you know, that's what he was like.
I only need this to see to get angry. So I was like, let me just not study.
I was sucky then.
Action on this semester.
Okay. Okay, I think I might have one. Okay, cheese. Okay, so. Okay, so or cheese.
I only
Okay. So, okay, so means cheese or cheese in Spanish. Okay, so if I'm finding the derivative of x squared plus 4x plus 8 or something, then guess what? So y equals, and then I have to use the limit definition, then I use as limit as h equals to 0 of f of x squared. I'm just gonna tell you it's a rational function. Or not rational, root. A root? That's gonna kill me. Dude, that's gonna kill me. I got it wrong, but I don't really care. Oh, okay. I did everything else right. Root, like x plus 1 or something.
e squared plus
Always makes 1. Oh.
Why did you use e squared plus 1 squared?
R squared. Fail. Looking for labs, that's not a lab. How do we solve this? You shoot yourself. What? Well, besides that. Okay, that is a really good example. That is very, very, yes, very good. I can't tell you because I failed it. But, you took it already? Yeah. The final? What? Why? What's learning? Because I'm gonna be in calc for like a little bit. Because swimming distance. I leave at 11:30. It's okay. It's easy. That's why I could teach you all this stuff. It's easy. It's legit. Okay, then help. Okay, so this is the one question I didn't get. But you understand it now? But I think I do. This trick showed me the answer and I can show you the answer. But I'm not going to show you the answer, but I could. I might. No, shouldn't. Okay, I'm going to look at his answer though.
Check my answer. Where's Justin Bauer? They're Justin Bauer for They're Justin Bauer. Say he's shoving them all.
Jeremy. I know the answer, Jeremy. You can't do this to me. Okay, I might only have one. Like, I'm pretty sure he handed it back to me and I didn't put it away. Ooh, this is one I haven't done yet.
Oh, it's because but that will be
Have you not done anything?
So eventually I'm gonna take the individual
Dude, I just made up this random question. Studying for the physics? What? I just made this random question off the top of my head. It's not, but it's close. It's very, very close. I bet it's excellent. That's why I said this is really good. That's why I said this is really good. Really good. I can, okay, yeah, so this is right. You have to multiply by the root conjugate. So you get x plus h plus 1 minus.
So it's a uniformly.
Wait, are you guys taking the.
Yeah.
Alright. take my time. Okay, how do you multiply this?
No, it's not really. It'd be related rates if like I told you that
Oh wait, but they didn't multiply.
back to time, so you have to determine how the density would change.
Oh, you're
Then
talking.
that would be related rates.
Whatever, man. It's gonna be pretty like pretty early. He doesn't start until 2. Alright. What period? What period did you pass?
So actually,
Are you right after us? No, you're not. Wait, for what? For how? I'm not talking about scale. For what? For this test. I don't know what you're talking about. We're talking about my next exam. Okay, so, okay. The exam is today. Oh, okay. Sorry, I didn't actually read. Okay, so, I aced my... Okay, that doesn't make sense. Yeah. Okay, cool. Well, I don't think it's back to the day. Better not go down to the piece.
sort of. Because well, like the main idea of fields is you determine the field. So charges create fields, then fields create charges. So once you determine what field is there, it doesn't matter what's creating it. If you want to know how a charge moves, the charge to do
Dude, I get this such a long thing, and I get it over H times root. What? H plus 1 plus X plus 1. Dude, I get this super long thing. Wait, when you multiply root by a root, should you just say root of these multiplied? Isn't that a thing? Can't you just say square root of x squared plus a... Something like that? No, because you have to FOIL it. Yeah, but I mean like... You do that to simplify? No, it should just be... You would want to simplify. Okay, I forget how to do algebra. I don't actually... I'm pretty sure you could... I'm pretty sure, like... I'm pretty sure root A times root B is equal to root AB. So you can just take this and multiply by this. I don't want.
Yeah, that's my fault. Do you have study hall today?
No. I have.
Okay. What class do you have next?
Yeah, because you're multiplying by 2.
Okay. And you're taking a final in there?
Yeah.
Are you taking both? Momentum and energy? Or just
It's,
energy?
you know the work energy power thing?
Uh-huh.
It's that one.
That one. Okay, so not momentum.
I think so.
I can look. I have all of it.
I can I think I can do the MCM. Because I've done all of them.
What's another thing you can say?
I did, wait, what's, I did chapter 9, 10, 11, that's,
Yes, that's momentum, work, and energy.
You have no idea what I'm saying.
Yeah, you just need to do that energy. So you only need to do this and this. There's the MC. And then if you get the time, it's those, just the circle ones. There's like 5 of them.
I figured out the median so I got an impression for attention. The only question is, when you're trying to set up the forcing the x direction, you have your the x component of tension is equal to the force, or is it 2 times that force?
No, it's just because they're separate objects.
I thought so, but I wasn't sure.
Yeah.
So, well, I mean,
Okay, so initially, okay,
I see what you mean. When you do this, what you're doing is you're using Newton's second law. Because you're saying it's not moving, so some force equals zero, and so therefore the tension equals to the gravitation force.
This times the electrical force, so it's whatever.
So when you do that, what you're looking at the forces on one object. And so that's why you only get one tension, one force. Yeah, I think that's right.
So I have field equals 2 Q over L, or L equal to A over 4 pi epsilon from 0 to 2L, because it's so much like everything. X over X versus Y squared.
yeah, what's the rule? What's the rule?
I don't get what
Yeah, so it's this time, so it's this square minus this.
L over 2.
So then we'll just get one.
Where L is equal to
L
2
minus
X.
X plus
So minus X minus 1.
so you get H.
It seems kind of when you already have they're like
Oh, I kind of forgot those names.
so you did from 0 to L over 2.
0 to L over 2, yeah, because if you take 1 point
And then you got
it's like a dramatic.
so where's the doubling effect here? Yeah.
Just integrate out here and put 2 over 2. That's so good to hear.
Yeah, about this way. He was playing Curious, he was for and then someone said we can do something. Oh yeah. And so they bunch of stuff. Yo, like you're telling me. And then you found it and you have a symbol of pretty much. It's not. I thought initially it was.
It's rewinding itself. If you were just teleporting, you wouldn't feel it.
Yeah. What the hell? Try it again. I tried it again yesterday. Maybe it wasn't on for long Yes. Okay.
What'd you do? What way? You used the
No, I was celebrating something else.
what are you celebrating?
What was question? I prefer these.
You think they do meditation, but I still think they're aren't there. I just
Okay, I understand. Here, let me teach you. Good. You don't need to learn. Well, are you drunk on chlorine water? This is difference of squares. So I can just, since this is difference of squares, I can just say this minus and then I get 1 over 2 roots. Okay, that's what I was confused about. Okay, that was somehow I still missed it. Are we allowed to on the whole ground? You're kidding. Seriously, it's easy. I never even used it. Dude, you can use it on the whole time. Literally? Okay. No, you never even need it. There's nothing hard enough for you. Okay, look, find absolute value, absolute max and min. Boom. If I forget, boom, 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 boom. Bro, that takes so long. Oh, oh, now I remember. The absolute maximum. Oh wait, no, that's wrong. You're high. You have to do the derivative. You have to do the derivative. Stupid. No, you're dumb. Stupid. You're dumb. Oh, this is weird. You didn't do the derivative. No, but I don't need to do the derivative. This is dude. No, I don't need to. I don't want to find critical points. Well, then find zeros. I want to find. Well, then just find absolutely. Then find zeros. Oh, yeah. No, see, that makes sense. It's the interval here. They're on 30. Yeah.
You can get that from.
Okay. Have you ever smoked? No. What is it like? It's a. You should try it. I should try it. Yeah. Sure.
I mean, I guess that's all. It doesn't all get you.
Dude, don't buy they give you a unfair advantage. So it's not based on skill and
Oh, well, let's see. Yeah,
search it up. You can, there's a detail below.
yeah. And I figured out how to do this one. The only thing I didn't get is you just assume this. Then you just use a tray.
I think it's just like
One of them is no landers. This one's required.
I know this one. Looks like a fun. Looks like this one. Oh. Oh, but it doesn't ever. What is that I was just not. No. Okay. I'm just.